Alright, welcome to our new method of delivering lectures. This is going to be over Chapter 5. Let's see, Chapter 5 through Section 7, I believe, is how far we're going to cover in this video, which is talking about circular motion and gravitation, mostly circular motion. Right. So, what we've studied so far is just linear motion, so objects, just like it says, moving in a straight line. We've also studied parabolic motion, two-dimensional motion, whatever you want to call it. Okay, objects moving like this. And now, finally, we are going to finish our kinematics unit with circular motion, objects moving in a circle. We're not going to cover ellipses or ovals or anything like that. Perfect circles are generally what we deal with in an APP. Right. So the first thing that needs to happen when we talk about circular motion is why this motion occurs. And it sounds like a really simple question, but it's actually a lot more misunderstood than you would expect by students. So if I am an object traveling in a circle like so, right, there's my little object. The question is, what is causing the object to move in a circle? All right, because if we know Newton's laws, we know that according to his first law, objects tend to move in a straight line. Let me write correctly. Move in a straight line. Oh my gosh, my brain's not working. Move in a straight line at a constant velocity. Right? Unless a force acts on that object. So this is obviously an object moving not in a straight line. So the question is, where is this force coming from, or actually, more specifically, where does this force point? Right? The answer is, to keep an object moving in a circle, the force has to point, if this is my object, the red dot, the force has to point into the middle of the circle. So regardless of where my object is, if I move it over here to this side, for example, here's where it was initially. If my object's over here, now the force must point still into the center of the circle. Right. So one question that a lot of students will get wrong, and even if they're really good at AP Physics, the question will be, an object moves in a constant velocity, right? In a straight, or not in a straight line, but in a circle. Is there a force being applied to that object? Or in other words, is the object accelerating? And the question is absolutely yes. Or the answer, sorry, is absolutely yes, because we know an acceleration happens when your velocity changes. Even though the velocity, I'm going to put delta for changes. Even though the magnitude of the velocity is constant, so if we're moving at 50 meters per second, for example, we're moving at 50 meters per second through this circle the whole time. It stays at 50 meters per second. My velocity changes because the direction changes. Right? So once again, if I go back to my circle, I can tell that my direction is changing constantly. I know that sounds weird. Whoops. But at every point in this circle, I have a new direction, right? Down to the smallest amount of time that you can imagine, my direction will change every unit of that time, if you want to think about it that way. All right. So I'm not going to take you through the derivation, but here's the first equation we're going to look at with a circle, object moving in a circle, and that's the acceleration of an object in a circle. There's a couple ways we write this. One is AR. I forget what the R stands for. Probably radial, since we're dealing with circles. The way that I write it most of the time is AC, right? The C standing for centripetal acceleration. Centripetal. Not centrifugal. Centripetal. It's different. This means center seeking in Greek or something. Doesn't matter. Right? So the centripetal acceleration of an object is equal to its velocity squared divided by the radius of the circle it's traveling in. And if you think about this conceptually, it should make sense, right? Acceleration and forces are very closely related. So if we're talking about the force needed to keep an object in the circle, right, pointing towards the center. Ooh, that's ugly. Let me fix that. Force has to point towards the center. There we go. We're talking about the force pulling the object into a circular motion, right? If the velocity of the object increases, right here, then you should realize that the force and the acceleration will increase. The faster I move around this circle, then the more my direction changes every second, right? Because I'm moving a greater distance every second, so my direction changes more. So that's the first thing. This goes up, the acceleration will go up, and the force will go up, needed to keep the object in the circle. The second part is with the radius. Right, this is an inverse relationship to acceleration. So if the radius decreases, right, if I make my circle smaller, then the direction changes less. Right, I'm not moving in such a great circle. So every second, my direction changes a little bit less. And then the opposite is true. If I increase the radius, then my object has to change direction a lot more in order to stay in that circle every second. Right, it's kind of like traveling a bigger distance in a way, if you want to think about that. Right, so this goes up, my acceleration, this goes up, my acceleration goes down. Right, wait, I completely explained that incorrectly. This goes up, my acceleration goes down, that's right, because I'm not having to change direction as fast. There's a greater distance that I have to cover. Sorry, I completely messed that up conceptually. So once again, it's very easy to get circular motion confused because it's not something we're used to dealing with. Let me draw you a picture again. So we're talking about the radius right now. Right. Smaller circle, there's my object there, and let's draw a bigger circle so we can look at how the radius affects the force and the acceleration needed to keep this object in motion. So the correct relationship is, right, velocity goes up, acceleration goes up, that's a direct relationship. Radius goes up, my acceleration should go down, right, and here's why. If I'm moving in a tightly packed circle like this, then my direction has to change greater. That's how I make a smaller circle, right? Instead of changing my direction by 20 degrees, I change it by 30, I get the blue line instead of the red line, right? Every second, for example. So here, on a bigger circle, you can see 1 second later, my direction hasn't changed as much as it would have 1 second later up here. Right, messy picture, but I think you get the idea. So radius increases, acceleration decreases, force decreases as well. Right. Couple of other equations that we need to work with is T, capital T. Remember, force tension has a lowercase t, time has a lowercase t. This is the first capital T we have. Capital T stands for period. We will see this later when we get to waves and oscillators and stuff. So T stands for period. It's measured in seconds, and this is basically how long it takes for the object to complete its motion. How long it takes for object to move in one rotation, right? Once around the circle. Right, that's period. There's another related term called frequency, which we denote with a capital F, or sorry, lowercase f, frequency. And here's the relationship between period and frequency, right? They are inverses. So period is equal to 1 over the frequency, and frequency is equal to 1 over the period. The way that we talk about frequency, it becomes more important with waves later, is that's the distance it travels in 1 second, whereas period is how long it takes to make one repetition of motion, in this case 1 circle. Right. And then finally we have a velocity equation for objects moving in a circle. So the circumference of a circle is 2 pi r. Okay. If we divide that by the time it takes to travel in that circumference, in other words, the period, we get the velocity. So that's a very simple equation, and one that you probably could have derived on your own without too much help. Alright, I need to take a break for a second, because I need to cook dinner. I'll be right back. Alright, continuing on. Your book in example 5.1 works out a problem using this equation, the concept of period, and I believe frequency too, but I'm not going to work it out. It's very simple. Same with 5.2. It just uses some astronomical values, meaning it's talking about the Earth and the Moon, so planetary measurements, which is interesting to look at, but once again, the math's really easy. I'm not going to go through it. Right, so in section 5.2, your book starts talking about dynamics of uniform circular motion. Right, dynamics is meaning measuring forces. Right, so according to Newton's second law, any object that accelerates has to have a net force. I mean, that's basically what his equation says. If an object accelerates, has an acceleration other than 0, it has a net force. Since we know our objects that are moving in a circle accelerate, since their direction changes, then we know that there's a net force, and we already talked about this. This net force has to point towards the center of the circle. I'm really bad at drawing that for some reason. Anyways, that force is going to point towards the center, and we call this, let me get the pen, we call this force a centripetal, I always have to think about spelling that word, centripetal force, right, center seeking. Okay, it is not a centrifugal force, which we're going to talk about in a second. Right, that's probably the force that you're more familiar with. It's not really a real force. Right, so it has to point towards the circle center in order to make it move in a circle. At any point in its motion, it's pointing towards the center. So the common misconception is that there is, if I'm moving in a circle, draw you another picture, instead of pointing towards the center, the misconception is that the force has to point, here's my object, the force has to point towards the outside of the circle. There's even a name for this misconception force, which is the centrifugal force. I'm not even going to write it down because you don't need to know it. Right? The centrifugal force is not a real force. Man, I keep forgetting which tool I have selected. It is not a real force. Let me write it down. I lied. Centrifugal. Okay. This force is not real. It is a result of the object's inertia. Right? When you move in a circle, you feel that you're being pulled to the outside of the circle because that's contrary to what your natural motion would be, right? Moving in a straight line. So you feel like you're being pulled outwards. That's the feeling of your inertia, your resistance to the force that's pointing into the center of the circle. It is not a real force, right? So based off of this, we can talk about what would an object do if it wasn't moving in a circle. So let's say we've got a ball on a string and we're twirling it around on this string. Right, here's a string. So we know the force keeping it in a circular motion is going to point towards the center. That's the centripetal force. All right. Let's say we spin this ball around in the circle, and when it reaches this point exactly, we're going to cut the string or let go of the string or something like that. What sort of motion would this ball have? Right. This is a horizontal circle, by the way, that we're spinning it in. Right. So the ball would move in a straight line. As soon as the string is cut, it moves in a straight line, and we describe this line as tangent to the circle. You should know that from geometry. Tangent to the circle. Right? So here's a great example of Newton's first law. Right? There has to be a force keeping this object moving in a circle, because if there wasn't, it would move in this manner, in a straight line. Right? So you can see every second how much the direction of the object has to change. Right? It gives you a good idea of how much force is needed to keep this thing moving in a circle. Right? So to calculate centripetal force, it's really easy. It's still the net force equation, mass times acceleration, except now this acceleration is specific. Right? It is now the centripetal acceleration, AC, A sub c. Right? And we remember this equation, A sub c is equal to v squared over r. Right? So it's the same sort of concept. We call it a different force. We'll label it Fc sometimes, but generally This force you don't draw in force diagrams. You're going to label it something else because this force doesn't exist on its own. Right? In this case, it would be a tension force because it's coming from the string. Right? If I was just pulling the ball in a circle using my hand, then that would be an applied force, electromagnetic force. Right? Your book works out in 5.3 an example calculating the force needed to keep an object in a circle. Once again, it's very simple. I'm not going to go through it. You can read that. Just briefly look at it. But it does, in 5.4, give you a pretty good conceptual example of what's going on here with circular motion. And I wouldn't be surprised if there was an AP question like this, because it's one of those questions where if you're not thinking correctly, you'll get it wrong. Alright, so basically it's talking about a game of tetherball, which if you've never played, it's just a pole with a ball on a string attached to it, a really simple setup. And you hit this ball around the pole, and the first person to hit it all the way wrapped away around the pole wins, right? And the question is, when this object moves in a perfectly horizontal circle, let me try drawing it. This is going to be bad. No, I want this still to be blue. Deselect. There we go. Right, when this thing moves in a horizontal circle, like so, around the pole, right, where is the direction of the acceleration? Right, where does it point, in other words? Right, most students will see the line pulling the ball towards the pole, and they'll say, oh, this force has to point, or this acceleration has to point this way because that's where the force is coming from, the tension force. Well, not exactly. Let's look at a free body diagram of this ball while it's on the pole. Alright, we've got gravitational force pulling it down. We've got some tension force at an angle. That's it. There's only two forces acting on this object. Right? So if you were asked to draw a free body diagram of this for an AP exam, this is what you would draw. No components. But in order to really understand what's going on, we do need to look at components. So I'm going to redraw this and put in the components. Gravitational force points straight down, so there's not a component with that. But we did have that tension force at an angle. I'm going to leave it as a dotted line because we're going to break this up into its components. Right? So with this tension force, there's two components. There would be Ft cosine theta here, the x component. And then you would also have the sine component here, which I didn't draw this to scale at all, but whatever. The sine component would be over here, but I'm going to move it to over here on my drawing so we can see what's going on. Ft sine theta. Alright, so we can say that two forces on this three-body diagram have to be equal. The ball in the y direction, the forces in the y direction have to be 0, because the acceleration in the y direction has to be 0. The ball's not, in other words, on this picture right here, the ball is not accelerating, up or down. Right? We said it's moving in a horizontal circle. So those two forces cancel out, right? This and this are the exact same. So where does the acceleration point? Well, these two forces are gone. I'm just left with the net force equaling cosine theta of my tension force, right? This would be net force equals this. So the acceleration has to point in the same direction, which would be towards, once again, towards the center of this circle, right? And not at an angle. It's a pretty good conceptual question right there. Alright. Let's see. Example 5.5 is a pretty good one. We may work this out in class, depends on how much time we have. But I would definitely read through this in your book. Basically what it's talking about is moving a ball in a vertical circle, and it's asking you to calculate the minimum minimum tension force to keep it in the circle at the top of its loop, and then the tension force at the bottom of the loop. Right? But what we're going to do instead on this video is work out a conceptual example that, without going through the math, gives you a similar answer. Right? So the book uses an example of a Ferris wheel, but I don't like using the Ferris wheel example because you don't move very quickly on a Ferris wheel, so the centripetal force you experience on it is not very fast. So instead I'm going to use a roller coaster loop. Okay, the question is here, so we've got a rider on this this roller coaster, and the question is, first for part A, oh no wait, it's just all one question. It says, is the normal force that the seat exerts on, on the rider, at the top of the circle, let's see, is it less than, more than, or equal to, let me get a comment there, or equal to the normal force at the bottom of the loop. Right, so is the normal force that the seat exerts on the rider at the top of the circle or the loop, is it less than, more than, or equal to the normal force at the bottom of the loop? So here what we're really going to look at are two free body diagrams, one for the roller coaster cart at the top of the loop, and then one for the roller coaster cart at the bottom of the loop. So let's look at the top of the loop first. Two forces acting on this object. We're going to have force of gravity pulling down on the object, right? We're also going to have, sorry, no, we're not going to add that in. Remember, centripetal force is a made-up force. It's just a name for a specific force. So in this case, the centripetal force is your gravitational force, and I don't want to draw it on there twice, right? And so that means the normal force is going to point up like this, right? So at the top, in order for me to move in a circle, right, this is at the top of the loop. In order for me to move in a circle, I have to have a force that points towards the center of that circle, right here. Okay. So, essentially what this question is saying is that at the top of the loop, the normal force and the force of gravity, here's the relationship. In order to move in a circle, the gravitational force has to be greater than the normal force. Right? If it's not, then I don't move in a circle. Those two things cancel out. I would move in a straight line. Right? I wouldn't accelerate. I wouldn't change direction, in other words. Right? So that's the first part of this problem. The second part of this problem is looking at the roller coaster cart at the bottom of the loop. So once again, force of gravity pointing down, and once again, normal force pointing upwards. Right? This case, though, the force that's keeping the object in a circle is no longer the gravitational force. That's not pointing towards the center, but now it's the normal force. So at the bottom of the loop, we get this relationship. The normal force has to be greater than the gravitational force to keep you moving in a loop. So the answer is the normal force at the top of the circle has to be less than the normal force at the bottom of the circle. You've experienced this if you've been on a roller coaster with a loop. Right? When you first enter the loop, let's say you're coming into the loop right here, the very first feeling you get is that you're being pushed down into your seat. Right? This is a direct this is caused directly by this normal force right here suddenly increasing in order to make you move in a circle. Right? We talked about how it's your inertia that you feel when you move in a circle, not the force. So the reason that you feel pushed into the bottom of your seat is your inertia is trying to react to this normal force pushing you upwards into the circle. And then once you get to the top of the loop, you feel almost weightless. Well, I shouldn't say that. You feel like you're starting to fall maybe a little bit out of your seat. The seat doesn't push as hard on you. That's because the normal force has decreased now. And so your inertia, the normal force points up, your inertia is going to point down, right? And so you start to feel that you're coming out of the seat. If a loop is perfectly set up to where you reach a speed very close to 0 meters per second here, which doesn't exist in real life, but if it was to exist, a velocity of about 0 meters per second at the top, you would feel almost weightless as you went through the top of the loop, right? It's an interesting little bit of trivia. Alright, moving on. Let me go back to page 1. So the next common physics problem that you see with circular motion is a car going around a curve, right? So let's say this is our track. There's our perfectly drawn car right here. Like I said, you see these problems all the time. They're like just as common. Incline problems with forces. This is the same thing. This is the incline problem for circular motion. It's a car in a curve. Let's see. How do we want to look at this? So let's look at the free body diagram of a car making a turn, right? We're going to assume this turn is perfectly circular to make the math easier, but obviously you can do this when it's not. All right, so here's the car. It's not accelerating in terms of magnitude of its velocity, right? So it's keeping a constant speed. That's the other assumption we're going to make. But it is changing direction, right? So we could look at this is a top view, by the way. We choose a top view of the car because we know in the side view, I can't spell. The side view, this looks like side neon. That's horrible. There we go. In the side view, it's a really simple situation where the normal force that we have and the gravitational force are equal and they cancel out. The car doesn't accelerate up or down, in other words, which we already know. From the top view, though, since the car is moving in a circle, we have to provide a centripetal force. I'm going to go ahead and label this as FC because we don't know what it is yet, but we do need to figure out what's causing this centripetal force. When you round a curve, you know you turn your handle, the steering wheel, and in order to make your car turn. What you're actually doing here is you're using the frictional surface you're driving on to make you turn, right? So this centripetal force on a car rounding a curve that's flat always comes from the frictional force, right? In other words, this would be, since we're on a flat surface, this would be equal to the normal force of the car times mu, right? In other words, Fg mu. So we can solve for a lot of things knowing this. Example 5.7 tells you the mass of a car, it tells you the radius of the curve it's making and the speed it's moving at. And it asks you, will the car make the turn or will it skid in two different situations. One where it's dry, the track is dry, and you got a static friction of 0.60, and then the other one where the pavement is icy, and the static friction goes down to 0.25. So look at 5.7. We may work out a problem like this in class, because this is a very typical circular motion problem. But the main thing is here, you need to realize on a car turning, the frictional force is what causes the centripetal force. And that's how we set up those problems. The next thing is a car on a banked turn. Alright, so same situation, except now our car is on an incline, which we all have incline problems. I know we do. Alright, car's on an incline now. So here's our car on the incline. In this situation, it's still a frictional force. Actually, no. You can have frictional forces in these problems, or you can't. It just depends on how it's set up. But let's look at it first without frictional forces. Right? What force is going to make this car move in a circle? Okay, so we know that the gravitational force, let me draw this as an actual arrow. The gravitational force is going to point downwards on this car. And that's the first force we'd probably draw on this free body diagram. Okay. Since we're on an angle, though, we know that the normal force is always perpendicular to our surface, so it would look like this purple line, about there, perpendicular to our surface. right? So now that it's perpendicular, we can look at the two components of this force. And if you remember our little convention, I'm not going to draw out the rules again, with objects that are on an incline, we know that the force that's going to make the car slide down the track is going to be sine of theta. Well, I got rid of my line, didn't mean to do that, my arrow. So this would be Fg sine theta, making the object go down the ramp. And then we would have an opposing vertical force going up the ramp. Not up the ramp, but perpendicular to the force of gravity, and this would be Fg cosine theta. Right? So if we're looking at the free body diagram, like I said, you never draw components on a free body diagram on the exam, but it's useful to look at it in this case. Force of gravity points downwards. That's not what's keeping us in the circle. Remember, the center of our circle is over here. We're on a banked turn, kind of doing this sort of thing, if you can picture that in 3 dimensions. Force of gravity doesn't point down into the circle. The vertical component of the normal force, Fg cosine theta, does not point down into the center of the circle. It is the sliding force, Fg sine theta, that causes you to move in a circle. So that's the first thing that you have to realize. On a banked turn, the sine theta of your normal force is going to cause you to move. This is our centripetal force, in other words. It's the thing that's going to cause you to move in a circle. If friction is involved, then we get a different situation. Because if friction, your car is going to want to slide, like in this drawing right here. Actually, let me redraw this because it's going to get confusing. Too many arrows. This is in a case with friction. Draw the car again. So our car is back on the incline. Whoops. With friction, it's going to be a little different. Still Fg pointing downwards. We're still going to have the sine theta of our force pulling us into the circle. But remember, frictional forces will almost always oppose the direction of your motion. In this case, it will oppose the direction of your motion. So the car is going to want to slide this way, right? That's moving out of the circle in a straight line. So our frictional force is going to point the opposite direction of that line here. So if we add friction to our ramp, now our centripetal force is going to equal two forces. It's going to be Fg sine theta, and then it's also going to be our frictional force. And we can break this down even further because we know our frictional force, based on our little ramp rule, is going to be equal to Fg cosine theta mu. And with those two relationships, you can solve any ramp problem, or inclined plane banked turn problem is usually what they're called. Section 5.4 in your book, I'm not going to cover this. If it shows up on the AP exam, it would be one question, so it's just not worth our time. It's really not a big part of our curriculum. Section 5.5 talks about centrifugation, which is something that you would use in a lab. Basically what this is talking about is we can use the inertia of objects when spinning them in a circle to split up some solution into different components based on their mass. So objects with a lot of inertia are going to slide to the outside of the test tube, while those with not as much inertia will start to slide towards the inside. They won't resist the force as much, right? So they get pulled into the circle a little bit more. That way we can separate things by their masses. It's useful in a lab, but it's not really anything you need to know. Section 5.6 is really what we need to spend the rest of our time on. And this is Newton's law of universal gravitation. This law is very old. He wrote this in the 1700s. Newton, by the way, was, I think I already mentioned the trivia. He was a mathematician, a physicist as a hobby, but very widely known as a physicist instead of a mathematician, obviously. But he invented calculus, which a lot of people don't know. Big deal, inventing calculus, that. So, Newton's universal law of gravitation dealt with he's observing mostly the motion of planets. You hear the apple falling from a tree story, which didn't actually happen, but well, we don't know if it happened. It's just a little anecdote. But he was looking at the motion of planets, and I'm not going to go through all of the stuff that he looked at, but I am going to show you that the first thing he realized is that the force of gravity between any two objects is proportional to, right, we can't say equal to at this point, it's proportional to both of their masses divided by the radius between them. That was the first thing that that Newton found out. And this was mostly done just by thinking and then experimenting later, but mostly just, this is a thought sort of process he went through. He knew that the more massive your objects were, either one of them really, then the force of gravity increased. So he said that has to be a direct relationship. And then he said the further apart these objects are, the force of gravity has to decrease. So that has to be an inverse relationship. So we can break this up into saying the force of gravity is, I don't even know if there's a symbol. Yeah, the force of gravity is directly proportional to the masses of the objects. Meaning if the masses go up, either one of them, the force of gravity goes up. If either one of them goes down, the force of gravity decreases. The force of gravity is inversely proportional to the radius squared. Whoops, that's important. Radius squared. So if the radius decreases, the force of gravity goes up. If the radius increases, the force of gravity goes down. That's an inverse relationship. So he knew this, but his calculations weren't coming out to be right. So what he assumed is there had to be some sort of constant, we're going to call it C, sticking out here. Some number that adjusts for the way we measure things in meters or kilograms or whatever. And so he found out this constant, which we label with a capital G. Right, this is the gravitational constant. This constant is equal to 6.67 times 10 to the negative 11, and I always forget the units. Let me look it up. 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. The importance of these units, is that this cancels out in your problem. So when we use this constant, it doesn't change the units of our final answer. We still get newtons as our final answer. So that's really the only importance of these units. You don't need to write them down when you use G. So finally, his Newton's universal law of gravitation is this. The force of gravity between any two objects is equal to our constant G times the mass of the two objects, m1, m2, divided by the radius between those two objects squared. That's his law of universal gravitation. It's called universal because Newton was the first guy to really declare that this gravitational force has to exist between all objects and not just planets. That was kind of the notion in his day up until that point. Obviously there's gravity between us and the Earth, or apples and the Earth, but a lot of people didn't believe that there would be a gravitational force between a person and an apple. Well, there is. It's very small because both of the masses of those objects are really small, but it does exist, right? And that's why it's called the universal law of gravitation. He was the first one to say that. Just a bit of trivia from Newton's work. There are really two things that could be explained. One is tides. Tides were understood in Newton's day, but there was one thing that we couldn't explain in terms of tides, and I'm just going to show you very quickly. Blue is the Earth, black is the moon. We knew that the moon caused tides, but we didn't really know how. So here's what happens with tides. Basically, when you have a tide, it happens when the moon is lined up over that portion of the Earth, right? So the one thing that most students know is that you get a high tide. I'm not drawing this correctly. You get a high tide on the part of the Earth closest to the moon. Right? So that represents the water of the Earth rising up to meet the moon. And this is pretty easily explained by Newton's law. This is obviously the gravitational force of the moon pulling on the water, and it pulls the water up off of the Earth. Right? That causes the tide. So scientists were pretty eager to explain that. It wasn't something that confused them, but here's what did confuse them. On the other side of the Earth, you also have high tide. So these tides come in pairs, right? So over here we also have a high tide, and Newton was able to explain this because of this part of his law. that the force is inversely proportional to the radius squared. Right, so explaining this part of the diagram, why there's a high tide on the direct opposite side of the Earth, of the Moon, it's because that water is a further distance away than the water over here and the water on the sides of the Earth. So what happens is you can kind of think of it sagging off of the Earth because the Moon is not pulling on it as hard as it pulls on the water over here, the stuff that's closer to the Moon, right? The radius is less, so the force of gravity is a little bit higher over there than it is on this side of the Earth. So the water sags and causes that other high tide. The other thing is, when we were still naming and studying planets, we had gotten up to, I can't remember. Anyways, scientists were studying, I think it was, I don't remember the exact planets. I think they were studying Uranus. Right? And they noticed that the motion of this planet was a little weird. It didn't follow the exact path that they thought it should. And scientists were able to use Newton's universal law of gravitation to predict that there had to be another planet near Uranus that was causing its path to shift somewhat. Right, the force of gravity of that planet was pulling Uranus out of a perfectly elliptical path, which is what planets travel in. And they called this planet Planet N. Hadn't been observed before, anything like that. They just said it has to exist, and we can prove it using Newton's universal law of gravitation. So these two scientists, I think separately, funnily enough, told the whole scientific community that this planet has to exist, and they basically said, go out on this particular night, point your telescope into this portion of the sky, and you will see a new planet that we haven't named before. It has to exist based on this law. And of course they were true, and this planet later was named Neptune. So just another bit of trivia. They were so confident in Newton's universal law of gravitation that they basically bet their whole careers and their confidence in science, I guess, claiming that this planet existed, not having observed it at all, and they just told everyone about it, and people pointed their telescopes in the sky and did see that it existed. So that ends what we're covering in Chapter 5 so far. We're going to work some example problems in class, and then the rest of the time will probably be spent on some practice problems, your homework. Whatever we don't get done in class is going to be your assignment for home. All right. Oh, don't forget to answer the quest questions that accompany this video in order to receive credit for this lecture assignment.